All right, so this we're going to be just kind of briefly covering the um, water quality components here. And that's not working. There we go. Very, generally about the water quality theory, but then when we talk about linkage to EFDC hydrodynamics, it's a coupled model, which has its advantages and disadvantages. Most of the time, it's a significant advantage to have a coupled model as opposed to a decoupled model. I don't know if anybody's talked about that earlier today, but we'll talk about it a little bit more later this afternoon. And then we'll talk about the user interface for the water quality. When we talk about water quality, it's really a eutrophication model, because water quality actually encompasses much more than just eutrophication. So we're actually looking at somewhat rebranding what it's called in EFDC. It's always historically been called the water quality module, but really it's the eutrophication module, because obviously toxics and sediments, temperature, these are all water quality parameters. But anyways, it's a minor semantic. Yeah, you guys can jump to these links to get access to the documents themselves. So let's just talk in broad terms about what's really the eutrophication conceptual model framework for the water column. You can think of it, I'm going to be talking about the water column first, and the kinetics and the processes that go on there. And then secondly, I'll be talking about the sediment diagenesis, which is essentially just decay of organic matter in the sediments that cause a nutrient exchange into the water column, which is really where we're typically most concerned about the water quality, at least from a eutrophication standpoint. So yeah, we've got the the different. Apologize for the colors. We're going to change these a little bit to make them a little bit more readable. They look fine. The white on dark looks fine, but the white up here is really hard to read. But anyways, so we have just in the way of kind of talk about the some of our abbreviations. You'll see a lot in the documentation. PON, particulate organic nitrogen. Then you'll see everywhere where you see a P in the beginning of an acronym, it's particulate. So that's particulate organic phosphorus, particulate organic nitrogen. Where's the particulate organic carbon? Actually, oh, there it is, particulate organic carbon. And then the D stands for dissolved organic nitrogen, organic phosphorus, and organic carbon. And then you've got your dissolved inorganic phosphorus or phosphate, your dissolved inorganic nitrogen, which is a combination. You separately simulate ammonia and NOx, which could be NO2 and NO3, just rolled up together into a single term in this model. And then, generally, kind of what is your end point on water quality? It's usually dissolved oxygen. That's really kind of the target that you're usually shooting for, but it also could be chlorophyll A, which is the net phytoplankton results that are in the water column. And we'll talk a little bit about how that's kind of built up here in a little bit. We don't actually directly simulate in the model chlorophyll A. We simulate the carbon component of the algal groups. So we've got 3 groups, and I'll talk about that a little bit more, but basically green cyanobacteria and diatomaceous algae. So we look at those 3 different groups right now and calculate a net chlorophyll A value based on some conversion factors. There's some standard EEMS. When you crank up a model, you'll see when we do it this afternoon with the hands on, when you initialize a model, it initializes with defaults, which is based on a database that we built up over the years. It's good. It's a good starting place. Not, obviously it's not a calibrated parameter, or it's not, the parameters haven't been calibrated to your application, but it gets you in the ballpark. There's a lot of parameters, such as the conversion factor between carbon in the algal groups and chlorophyll A. That ratio is somewhat standardized. And we initialize it, but you can change it, of course, if you have site-specific information. So you've got all these, processes. These are the kinetic processes that are going on inside a single cell. But of course, you also have advection and diffusion processes, source and sinks, which we'll look at here in a little bit on the a little bit in the theory. But yeah, and then with respect to the processes at the surface, you can have wet and/or dry deposition fluxes coming into the water column at the top layer. Then you also have reaeration. Now, actually, this shows this is a one-directional arrow. Actually, it's bidirectional. So if you're supersaturated because of, say, an algal bloom, and you're in excess of saturation for your oxygen, that actually you lose it at the surface. But anyways, it's a surface process here. And then the effect of solar radiation and light attenuation, which affects both the heat submodel, but in the DSI, in the EFDC plus, we've coupled the algal components and organic carbon components into the light extinction, so you can have, it's a much more dynamic process calculating light extinction, which affects the growth of your plankton. So, and anyways, that's the it's a very coupled model between the hydrodynamics and the water quality, which is really nice. But of course, that means you pretty much have to run them simultaneously. You can't decouple them if you want to actually link the feedback from the water quality back into the hydrodynamics. So anyways, you solve the kinetics in the water column, and then you follow that by calculating the diagenesis processes if you're simulating a full diagenesis model. Using what we use is the DeToro 2000 reference, those equations in that reference to calculate all the nutrient processes and ultimately nutrient exchange between the water column and the sediment bed. But what happens is that your plankton and your particulate organic constituents, they settle onto the sediment surface. That actually acts as a source term to your diagenesis, and then you have the decay process, and some of that material gets released back up into the water column, but also some of it gets buried permanently, and there's a burial term that you can specify in the diagenesis model. You don't have to model diagenesis; it's optional. Even if you're going to model water quality, you can just ignore the sediment bed processes completely, just set everything to 0, or you can specify spatially varying and spatially and temporally varying fluxes manually if you want. But we found that actually the sediment diagenesis model works really well with some basic, relatively simple parameterizations. If you have organic carbon, total organic carbon in your sediment bed at a number of places, using that and standard ratios between organic carbon, organic nitrogen, and organic phosphorus, the Redfield ratios, you can estimate all the, your major drivers in your sediment bed for your initial conditions. Anyways, yeah, we'll talk about that at the end of, more toward the end of this lecture. Let me think if there's anything else that we need to say about that. Guess not. So I said there were 3 algal groups. There's actually 4, but the macroalgae is not a floating algae. It is an that's your attached algae. That's your periphyton, where the slime on the rocks. It can be and has been used to simulate actually, plant growth and things in the water column. Problem is, I mean, it's a simplistic approach, but it does work. Especially, most of the time you don't have any data, so you're just kind of, it's a broad brush to kind of get your algal and DO to behave in the model domain. But these 3 are all the standard phytoplankton, floating algae that move in the water column. You can apply a settling velocity to it, so that as they grow, they also settle, and eventually they'll settle out on the bottom. In the next version of EFDC Plus, we're actually totally generalizing all the algal groups, so that you can specify any number of algal groups up to 20 if you want. If you're doing a particular research project with algae, or more typically, maybe collapse it all down to 1. So you don't need to mess with algal groups that you actually don't have any data for and you're not really interested in. So that'll be in the next iteration of the water quality or the eutrophication model. With respect to the carbon constituents, we're breaking all of the organic nutrients basically into 3 broad categories. Refractory, that's your slowly reacting material. Then you have your labile, which is your fast reacting material. And then you have dissolved. And then depending upon if you're looking the other nutrients, it'll be, this one's carbon. We'll look later at phosphorus and nitrogen, but they're the same basic concepts. Then within the refractory particulate, both of these classes settle, and of course that one does not. That one just moves in the water column. And then right now, there's no inorganic carbon, and eventually we hope to get to next year having CO2 in the model along with alkalinity, and then we're going to be able to simulate pH. So that's actually in our development plan for EFDC Plus. So then we've got the other constituents, the nitrogen and phosphorus, the same, as I was mentioning, the same basic classes. There is issues around this is basically what's known as the ICM kinetic model. It was developed by the Corps of Engineers many years ago for the Chesapeake Bay by Carl Serco and others. Widely used. It's used in the C=W2 model. It's used in EFDC Plus. It's used in, I think they've got modules in for CH3D that are linked up at the core. Different hydrodynamic models have been coupled with this this module, and it works well. The one kind of issue around that is these are not standard water quality variables. So, well, we'll look, actually, why don't we do this? Yeah, this is probably a better way to look at it. So these are we have 21, if you will, state variables. These are all what I was referring to. So your particulate, organic carbon. So this group here is your carbon group, your nitrogen group, phosphorus group, and your silica group. Silica is only needed to be simulated if you're simulating diatoms. If you don't simulate diatoms, there's no reason to simulate silica, because it's linked into the growth of the diatoms, this class here. But then the R and the L stand for labile and refractory. See, where was I going with this? There's 21 variables. Oh, well, it'll come to me as we talk. A couple of other little things to note here. This is a chemical oxygen demand, COD. It's one of the state variables. But you'll notice that kinetically, it's not connected to anything. It's a kind of along the side. It could represent anything that has some oxygen demand, where you can apply a temperature-based rate kinetic term to it. Many times it's used to kind of simulate some instant or more quickly reacting metals with your active metals, but it could be other things. Anyways, there are ways that you can produce a water quality. Oh, I know. That's what I was talking about. Measured water quality variables versus the variables that we actually have specified here in the actual kinetics of the ICM model. We have in our documents typical ratios, like let's say you go out and somebody collects biochemical oxygen demand, or BOD, and then they have BOD 5-day, BOD 15-day, ultimate BODs, carbonaceous BODs, nitrogenous BOD, these different forms of biochemical oxygen demand, how they kind of roll up into these different terms. To help, you have to take what actually the lab data that you have and convert that into the actual state variable values. And yeah, there's a lot of guidance that we have, and there's other guidance out there in the literature to help you do that. But you don't typically get a lab to tell you, oh, how much refractory particulate organic carbon do I have? The lab won't give you that. Most labs won't. Some research labs will, but most of them won't. So anyways, you have to build these up through typical ratios. That said, this is where I was kind of coming to on this COD value down here, is if all you have is BOD and you're only interested in BOD, DO, and well, basically BOD and DO. Like a typical stream, like you have a wastewater treatment plant loading into the stream, you can build a really simple DO, like a Streeter-Phelps model. If anybody familiar with that simple analytical water quality module or model, you could build a Streeter-Phelps model just with these two and parameterize your COD as your as your BOD, and then your BOD interacting with DO, and you can get DO sag downstream, because the model by default is simulating all of the reaeration processes and decay processes. You've got temperature already there, and so yeah, I mean it's a simple water quality model, but it works. And it's on what your needs are. So, moving on. So this is kind of showing you the processes that are connected to the different algal process, in more of a process term as opposed to just the state variables. So growth consumes ammonia and consumes NOx. And in combination with light, and of course also consuming phosphate, and with light you get through photosynthesis, you grow your algal groups here and you produce dissolved oxygen. Respiration occurs 100% of the time that you have algal groups, regardless if you have photosynthesis or not. And there you're consuming the algal material is consuming the oxygen based on the amount of mass that exists of your algal groups. Predation. Again, the way it's predation, which is essentially, it's like, predators. I mean, you've got zooplankton, which we don't explicitly simulate zooplankton right now in EFTC Plus 10.1. It's either going to come out in 10.2. We're actually actively building a zooplankton module right now for EFTC so that people can simulate this more dynamically. But the way it works right now is you specify a rate, and that rate of predation consumed decays or breaks down the algal groups. And as it breaks down, it produces refractory, labile, and dissolved components for all of your nutrients based on the stoichiometric ratios for the different nutrients in the different groups. So things are being eaten, it gets distributed back into the water column, into these different components, and everything just kind of cycles back through. So you can see there's just a lot of interaction that's going on in these water quality models, which is, it's a food web in the water column for the, for the algal and or protozoa and everything in the water column. So the next item, basal metabolism. Again, it's kind of like respiration, except for this, in basal metabolism, it actually consumes mass associated with the organism, whereas respiration just consumes oxygen. So, but this is a 24-hour, 7-day-a-week process, as is the basal metabolism rate. Basal metabolism rate varies with temperature. As water cools down, their metabolism slows down. Basal metabolism production of or loss of the biomass here and production of these other state variables slows down as temperature drops. You'll notice that with basal metabolism, as opposed to predation, they both reduce the mass of your organic constituents. But with basal metabolism, it only produces the dissolved phase of the constituents. So you're only coming up here to your inorganic dissolved constituents and your dissolved organic carbon, dissolved organic phosphorus, etc. All right. I'm sure you guys have absolutely no questions. Totally clear, right? So we'll move on. So, as I said, basically the water quality model is coupled back to the hydrodynamics. It's not a one-way coupling. It's not just from the hydrodynamics to the water quality, because the water quality, predominantly with respect to the extinction coefficient, affects solar radiation penetration, which affects the hydrodynamics. So it is definitely a two-way coupling, but certainly stronger from the hydrodynamics to the water column. You've seen these equations numerous times today already, so I don't necessarily get into it, except for here on the source term, we have the internal sources, which is all the kinetic processes, and the external source and sinks, which of course are your boundary conditions and atmospheric loadings and things like that. And it's a fractional step approach for how it solves those equations. And basically, let's see here if there's anything there you haven't seen already. Diffusive transport, then your kinetic processes, which is what we're going to be talking about. And I think that's good there. physical sources and sinks, yeah, it's just, like I said, all your inflows and outflows. It says volumetric, but also you've got your atmospheric loadings in addition to your inflows and outflows. And let's see if there's anything. Oh, I won't talk about it necessarily. Well, I'll just mention it here. The kinetic rate, of course, you specified all your kinetic rates in the equation. However, water quality kinetics do not operate at the same time scale as your hydrodynamics. So your hydrodynamics are typically on the order of just a few seconds or less to solve your the hydrodynamics. You don't want to be solving your water quality at a 1 second time step. There's just not enough happening in 1 second, for one thing. But then also just the computational burden of doing this over and over again at a 1 second interval. So in EFDC Plus, you actually have a kinetic time step. So every minute or every 5 minutes, then you solve the water column kinetics. However, every single time step, you are solving the transport equation. So all the material is moving around, being advected and diffused, but at only whatever user specified interval are we actually doing the kinetic time step, so that it just really, helps in the computational speed of the model. There is, in the you saw on the links at the beginning, we've got the theory document, all in one place. We're continuously updating it. That's the best place to go for reference to get more information about the theory side. And then, of course, the user guide for EE itself will provide more input on what I'm going to show here on the user interface. So, just like all the other constituents, we haven't shown how you get to this step, but you go to that modules tab, right mouse click on the modules tab, turn on the water quality model. Once you've activated the water quality module, this, wrong button, you can get access to the editing form here. And this, I'll just step through it, but you've got your basics across the top. Let's look here at the, this is kind of the primary option for water quality. This option 1 here is actually the ICM eutrophication model. There are no other versions of the water quality model available right now, but it's been designed to allow us and or other users to build their own water quality module if you want. In the code, you could do it inside of EFDC, and then you would access it here by specifying module 1, module 2, module 3. That said, we're working with one of the researchers in Korea to develop a new water quality module. It'll be water quality module 2, which will include all the zooplankton and algal groups, as well as other updates and modifications to the ICM model. So that'll become module 2. But right now, module 1 is the only one that works. If you select anything else and try to run the model, it'll tell you, yep, this hasn't been, basically don't do it. That's what it'll tell you. So next thing, the number of parameters. As I mentioned, there's 21 state variables of the water quality parameters. And but they all don't have to be simulated. So there are many cases where you have some minimum set that you want to actually simulate. So the actually activate and deactivate individual or specific water quality parameters, you just click on this parameter button here, and it brings up this list here of all your constituents, and then a flag. 0 means no kinetic processes, no water quality transport. A 1 indicates that it's going to do both kinetics and track that constituent in the water column. If you're going to do just a standard, a relatively simple ICM eutrophication model, you need at a minimum 14 constituents have to be simulated. Like in this case here, all we want is we're just going to simulate 1 algal group, green algae. But to do that, because of the way algae interacts with the different nutrients, we have to have all the organic carbon options turned on, all the phosphorus options turned on, organic and inorganic, all the nitrogen turned on, organic and inorganic. Notice that we don't have silica turned on because we're not simulating diatoms. Chemical oxygen demand, as I mentioned, since it's kind of a standalone thing, optionally turn it on, turn it off, depending upon what your particular needs are. And then, of course, you need dissolved oxygen. So if you count those ones up, 14 parameters. And that's pretty much the minimum that you can, if you want a full water quality, but not maybe, research grade water quality kind of constituents. You've been running, I guess, temperature and dye. So your model's just running with 2 constituents. Now, with this, you got 14. Basically, 14 times longer to run the model. That's not completely true because it's only the advective transport. But as you start throwing this many constituents at it, the advective transport begins to by far dominate your run times. And so it has a significant effect on run times. And then kinetic processes also added, but because you can control how frequently the kinetics are updated, it's less important. It is important, but it's just not as important computationally as specifying the number of constituents. Let's see here. We've tried to generally group these forms up into what's kind of logical groupings. When you actually look at the input file, it's obviously it's much more convoluted than this. But the kind of your main options that you may be making a lot of adjustments to during the course of your model setup and model calibration process are kind of defined here in a group of water quality constituents that you can spatially vary. And that's what they mean by zones. So if you've got one zone, then that same kinetic rate, say, 0.1 per day decay rate, it gets applied everywhere in the domain. But you can break up the model by kinetic zones, and this isn't just horizontally. You can have vertical zones too. I can specify layers, the bottom layer up to, say, layer 10 is zone 1, and then layer 11 through 13 is zone 2, etc. So it's both horizontally and vertically zone assignment is available. And so it's quite flexible in that sense. You scroll through your zones here, and whenever you click on a zone here, and then you click on any of these buttons, if you've got, there's a lot of interaction. You got to really pay attention to this. Again, we try to simplify it as much as possible, but even if you've got 10 zones, it will only apply the zone if you turn on the zone option. So I could have 10 zones and only use it for my algal dynamics, not use it for my settling, and not use it for these other kinetic processes that are in this button here. So yeah, it's just, it's very flexible, but if you start throwing anything much more at it than just a single zone, you just have to really be aware, be careful with, with your assignments and stuff to make sure that you're assigning what you think you're assigning. When you hit define zones, EE has a resource, a tool that allows you to provide these, three-dimensional zones definition. And it has some QC stuff in here that says, oh, you've got this area here that doesn't have any zone assigned. This area has zones, these don't have zones. Of course, it won't tell you that an area has, if it has an assignment, it considers it okay. It doesn't, that's your job to make sure that the assignments are correct. But EE just checks to make sure that something is assigned if you're using zones. Just some of the parameters when you press those different option buttons back here, these modify buttons. So you've got your, what we call this general kinetics, settling, and algal dynamics. That's what these three dialog boxes, each one would bring up. It will inform you as to what the zone that you're currently editing at the top, and then here's the different parameters that are available for adjustment. Probably the ones that you're most, well, if you're simulating COD, these numbers down here, can be, you might be making a lot of adjustments to those. But if you're not, then, you're probably just more focused on, say, the reaeration approach and coefficients for the different zones if you've got multiple zones. So that's the kinetic parameter button, your settling parameters for each of your different algal groups, and then your particulate constituents for all particulate organic matter. That's all three classes. And your labile organic matter for all three classes, etc. TAM stands for total active metals. And a lot of times you don't need to simulate it, but it interacts with phosphate. So sometimes it's useful if you want to have active metals interacting. And basically, total active metals can provide surfaces for dissolved phosphate to attach to, and basically take it out of the water kinetic processes, and then it can be removed because if it's attached to the metal and then the metal settles, it basically strips the phosphate out of the water column, if that's appropriate for your application. And then your algal growth parameters here, it says growth, but these are the growth parameters. These are your growth rates in per day. But then down here, you got your basal metabolism rates and your predation rates. And then you have a background light extinction coefficient that is added to all the rest of the computed light extinction from your other water quality parameters. Nutrients, we grouped them again, basically by the major groupings. As I was mentioning about the total active metal here, this is relative to phosphate only. So for phosphate, if I don't want to mess with absorption of phosphate to any solid, I just can select none, or I can optionally have it sorbed to total active metals, or I can have it sorbed to cohesive sediments in the water column. if you turn cohesive sediments on in the water column as a flag, but you're not simulating cohesive sediments in the sediment transport model, then it won't do anything. It doesn't tell you got an error, because it's not an error necessarily. It's just there's nothing to sorb to. So nothing would happen. Algae, yeah, we just kind of, again, now when you click on some of these buttons, like the algal dynamics here, it's going to bring up something that looks really similar to this, because it is. These are by zones. The default value associated with it, which is zone 0, is what's you can select here. So if I click on the algal dynamics, it'll say zone 0, but it'll be the same parameters that you had in the other one. Let's see, stoichiometry, that's where you get all your ratios of carbon to nitrogen for your breakdown processes. You also have that ratio between carbon by algal class to chlorophyll A. And it's all by the default. We got values for all of this, but anyways, this is where you access it. You'll find that as you kind of get into these water quality models that the temperature, I mean, it is super critical to get your temperature sensitivity right. And we've got tools to help identify, or at least visualize your inputs that you're putting into the model, kind of make sure they make sense when you're parameterizing and calibrating. Let's see here. Have saturation constants, which affect growth rates and breakdowns and etc. Oh, this is a important flag. Basically, this is going to couple your solar radiation to the algal growth. There's a lot of algal growth kinetic processes or theory out there that kind of look at algae growth on a daily basis, but it doesn't account for diurnal fluctuation of light. And so if I use this source constant a constant solar radiation source here, there's no difference between day and night growth. If you plot up a time series of growth, it'll just be growing and changing based on the temperature and advection and diffusion and settling and all that kind of stuff. But you won't see any effect of night day conditions. So just be aware that if you drop down this, there are four options available for doing solar radiation. Constant. You can have a user define what's called a sunday.imp file, where you, outside of EFDC, manipulate some solar radiation data and build up your average daily solar radiation value that you're going to input to the model, and the fraction of available solar radiation during the day. And then the other two options are basically options where it uses the ACER data that you've already provided for the temperature model, and then processes it into the appropriate inputs necessary for the water quality module, that's what we typically use. When in a real application, because we have solar radiation is crucial to your temperature model, and you have to have temperature to do water quality. So we usually just turn on option 2, which is allowing for hourly solar radiation variation. This last one is the solar radiation fraction for the photosynthetically active radiation. It's actually more typically around 0.43. This is an old value. But when you're specifying as a hard-coded constant value, you could just set that to to 1, and that would just actually should reflect the actual solar radiation that's being used to grow the algae. So the algae can only use the photosynthetically active range of radiation. So yeah, it just takes that number times that number, and that's actually what goes into the equations. But if you're basing it on measured data, these two are nice because then you can directly correlate, oh, that was my average daily data, and this is the actual PAR for that region. So ties back to data better. Initial conditions, just like all the other water column parameters, you've got everything from constant to spatially varying vertically average to full 3D vertical profiles, spatially varying, vertically varying. Yeah, just a lot of options. Now, this next option here, I want to ask, has anybody actually ever used the ICM model for anything, either inside of EFDC or outside? Because the ICM model up into EFDC Plus used you had to externally calculate your boundary conditions and loads in kilograms per day. Even though we have flows, we have a boundary condition, you got a river, it's coming in, I know the concentration and I know the flow, that's what I want to provide to my model. I want to provide a concentration and a flow rate and let EFDC calculate the actual mass loading. Because, that's just physically based. You go out, you collect data, I know what my concentration is, so it's easy to make that conversion. So all the other boundary conditions in EFDC use that combination of flow and concentration. The original version of the water quality model did not. You had to specify a mass loading in kilograms per day, and it was completely decoupled from the actual boundary condition. So you could actually have, a mass loading coming in and there's no flow coming in at all. Different things that didn't make any physical sense. So we have, by default, when you build a model, EFDC Plus and EE allows you to use the same approach that all the other boundary conditions in EE use, which is flow and boundary condition. Flow and concentration. But if you have legacy applications, you might need to use the old one, and we support both. The data is stored in these files. That's actually supposed to be WQ. I just noticed that. That's actually a bug. WQ, point source load concentration, WQ PSLC. And if you're using mass loading, it's WQ PS, water quality point source load, PSL. So if you see a file in EFDC project folder, WQ PSL, that's mass loading in kilograms per day. If you see a WQ PSLC, it's concentration based concentrations in there anyways. And then here, atmospheric deposition for wet and dry. Again, as you would expect, wet deposition is entered as a concentration because it's the concentration of the rainfall. So if you have no rainfall in your ACER file, then this won't do anything, even if you put 1,000 in there, because there's no flow essentially to multiply times your concentration to get your mass loading. But the dry deposition, 24/7, kilograms per meter squared per day, flat rate. One doesn't change in time or space right now. So if that is, you just got to be really careful with that. Make sure that that's either 0 or it's a number that makes sense, because you can just artificially load your model with all kinds of mass if you're not paying attention to what's in your dry deposition term. One other kind of thing that's a little bit awkward, time series data. There are 21 constituents in the water quality module. And the WQPSL file for the point source load here is based, all 24 constituents are all have to be input at the same temporal resolution for every constituent. So if you've got, hourly time step for DO, you have to have hourly for everything. And so what happens is when you edit a time series in EE and in EFDC, you got to be aware that if you add change temporal resolution for one constituent, it rolls through all the others. EE should and tries to make sure that if you insert a row for DO, there's a row inserted for all the other constituents and automatically interpolates between the data that exists on either side of that parameter. Likewise, if you delete rows, it should delete the row for that same row for all the other constituents, etc. But at the end, when you get finished, you have exactly the same number of snapshots, and they have to start and end at the same place for a series. However, you can have any number of series, like a major river. So you've got, the Mississippi River coming in, and then you've got the Illinois coming in on the side. Then, they can have two completely different time series, two completely different snapshot frequencies, whatever you want. But within a series, they're identical. Now, the benthic, this is the sediment diagenesis. This is where you specify benthic fluxes. And as I mentioned, there's three basic fluxes, three basic options: spatially and temporally constant. So you get one nutrient flux everywhere at all time, or you can have a number of diagenesis zones, and they can be temporally constant but spatially varying, or they can both be temporally and spatially varying, user specified. But we typically either use one, either constant at 0 or just some low value, whatever's appropriate, or we go full on sediment diagenesis using the DeToro 2000 option. And you specify all those parameters in this with this button, modified parameters. I don't think we have a module on the rooted plant and epiphyte, but notice it's in the water quality module, because rooted plants basically are only there because they're interacting with your water quality. It makes no sense to try to simulate, plant growth and death, and interaction with the water column, which is what this rooted macrophyte module does here. If all you're interested in is the hydrodynamic impacts of plants on, well, the impact of plants on your hydrodynamics, that's the vegetation module, and Wei Chen will be talking about that on Friday. However, that said, right now, there is no interaction. This is there's two kind of caveats I'll make here about the water quality module. The water quality module does not interact with the sediment bed, or especially, I mean, the sediment diagenesis does not interact with the sediment transport model. So if you get a big flush of bed load coming in and you got 2 meters of bed load that just, came in and covered your bed from some big storm event, water quality model, totally unaware. It's just cranking along, just totally ignoring what's going on in the sediment transport module. That is something that we need to address, but typically you're not generally simulating a water quality module with a really active sediment model. They're usually, if you're simulating sediments, it's more just kind of TSS, a little bit of TSS, you get some deposition, you're not really too worried about it. But just so you know, they're decoupled from the sediment transport model. And then rooted macrophytes, which are rooted plants in the water column, I mean on the bed, growing up into the water column, they have no impact on the hydrodynamics, and that's probably not valid either. There needs to be some feedback. If you've got a really dense growth in your water quality module, calculated as a result of rooted plants, there should be a feedback back into the hydrodynamics. But right now there's not. All right. I could jump in straight into the benthic stuff, but why don't we take a break and do some hands-on.